All right, everybody. So today we're going to do applied optimization. What that means, okay, first off, applied means using something. What is optimization? The most efficient. Yes, you can say that. Yes. Example, you're hired by a company to design a box for their new toy. If you think about it, I mean, a box is just a box. But for example, for my little camera here, the insides are what's impressive. I mean, look at this thing. All this stuff has to be cut from one piece of paper. That has to be done mathematically first. Is it possible? Can it be done? If so, what is the smallest piece of material we need to complete our task? So that way, the smallest piece of material costs us less. So let's look at example one. An open top box. Is to be made by cutting small congruent squares from the corners of a 12 by 12-inch sheet of tin. And bending up the sides. So the question is, how large should the squares be? The squares cut from the corners be to make the box hold as much as possible. This is a real world example. So we have to take that statement, that question, put it into a picture that'll help us put it into a formula that'll help us solve it. Always, always, always go to a picture. So what do we know? We have to design an open top box. It has to be made from a square sheet of tin, 12 inches by 12 inches. So that means we have to cut congruent corners, squares, on each side, each corner. How large should the square cut from the corners be? Do we know how big they should be? No. So we call them X. Since they're square, they're going to be the same on both of those sides of that little square. So what exactly are we looking for? We have this now. What formula are we looking for? Hold as much as possible. The box hold as much as possible. So what does that mean? What are we looking for mathematically? Volume. Yep. What's the formula for volume? Base times width times height. Because you have the base, you have the width, and you have the height. That's the volume. Or another way you could say the equation for a volume is area times height. Because remember, area is base times width. So far, so good. So what area are we looking at? Well, the area is going to come from this sheet of tin. What are the dimensions of this tin after we cut these corners out? So what is the length of this side? This is the base. This is the width. So what are the formulas? What is base? We know it has to equal 12, but we cut out these corners. Ooh, y4x. You're close. Because we're looking only on this side here, looking that way. Where is this x? It's up and down, so it doesn't matter. So it's 12 minus 2x. You're close. What's width going to be? Same thing. So the area is base times width, which makes it 12 minus 2x squared. That's the area part. So all we know about our box right now is it's going to be 12 minus 2x times 12 minus 2x. How high does it go? If we cut these and we fold the corners in, how high does it go? X. Because if we fold it here, and it's X units. So our volume is base times width times height, which makes it 12 minus 2x squared times x. That's our volume. What do we do next? So what's our equation look like? What can we do with this equation? Okay, well, that's a good point. If we solve for x, what good is that going to do? No. Let's look at, if we take x, both x's, so we have x equals 0 and 12x minus 2x equals 0. So this is 12 equals 2x divided by 2, x equals 6. What these two values just told us is the domain of x. Our x's have to be between 0 and 6. But would you really use 0 and 6 as values? What happens if you put in 0 or 6? If x was 6 inches, if this was 6 inches and this was 6 inches, you just fold a piece of paper. If it was 0, then you just have that. You wouldn't have a sheet. You would not have a height, so your volume would be 0. So what you're looking at here, these would be negative. These would be 0. So let's look at our equation and let's expand it. We would get 12 times 12 is 144. 12 times 2 is 24, 22, 24, 24 is 48. Plus 4x squared times x. And distribute that little x into everybody inside there. We get 4x cubed minus 48x squared plus 144x. So that's our formula for our volume. So far, so good. So how do we find the optimal volume of this thing? Or if we were to graph this, what would the graph look like? It's a cubic function. So it'll look something like this. So what we're looking for the extrema, because that's going to give us the x values that give us the highest volume. This is why I hate this room. So what we have to do, since we know our function equals 4x cubed minus 48x squared plus 144x. To find the extrema, what do we do? Very good. Good question. The extrema are the maximum minimum. The places where the slope is zero, so it's first derivative. The second derivative tells us where the bending stops being concave up and starts being concave down. So it's a change of concavity. That's what they call a point of inflection. So we have to take the first derivative. We got 12x squared minus 96x plus 144. Then what do we do? Because now it's the slope. We want the extreme. What's the slope at the extrema? 0. So we set this equal to 0. We can factor out a 12 out of there. Now we can factor out what we have left. What are the signs going to be? To determine the signs here of factoring, look at the second sign. Well, if it's a positive, it has to be the same sign. It's whatever the first sign is. They're both minus. Because a negative times negative is a positive. Positive times positive is a positive. So it's whatever the first sign is, it has to be inside there. Take the first and last coefficients. 1 times 12 is 12. So what times what equals 12? When we add them, we get 8. Set both of those equal to 0. So what do we know about these two? If x equals 6, what do we get? Yeah, we get that foldable, so we're not going to use that. So the interior point x equals 2 is the only viable answer we have for this question. So we're saying that the x equals 2, it will give us our maximum volume. So that's our critical point. So our critical point value is where V is when x is 2. So V is equal to, we can factor out a 4. We're going to factor out a 4x, which is going to give us x squared minus 12x 36. So plug in 2. We get 4 times 2. 2 squared minus 12 times 2. Four minus 24 plus 36. Negative 20 plus 36. So it's 8 times 16. 8. So the maximum volume will equal 128. How do we know this is the max? Remember, in the last chapter, whenever we have a closed interval and we have an interior point, to find the maximum, we have to find all three numbers. We have to find the interior point value. We have to find the endpoints. Remember that? So not only do we have to use 2, we also have to check the other ones just in case. But we know that when x is 0, the volume is 0, and x is 6 is also 0. So we know that x equals 2 is the shape of the box that's going to give us the most area, most volume. Right. We know that because, yeah, the reason the domain is x has to be between 0 and 6. And we know inside that interval, the endpoints may be the max extrema or this internal point that we did up here on top, where the slope is 0. We have to try all three of them. Or if we also have more than 3, we can have 7 or 8 of them. All right, let's change the picture. Example 2. You're asked to design a 1-liter can shape one-liter can shaped like a right circular cylinder. What dimensions will use the least material? We're looking for the least this time. Okay. First step, draw the picture. What is it telling us? You're asked to design a 1-liter can shaped like a right circular cylinder. What does a right circular cylinder look like? What is a right circular cylinder? What does right mean? Right angle. Has to be 90 degrees. It's got to be circular. And it's got to be a cylinder. Like a piston rod. Piston. What's that? Yes. Now, what are we looking for? In other words, we have to design a can. We're using the least amount of material. So what we have to do, we have to figure out how much material is used for the outer shell, how much material is used for the lid, and how much material is used for the base. So let's look what this can is made up of. It's made up of 2 circles, one top and one bottom, plus a sheet that goes around the can. It's a cylinder though. As a can. So what's the formula for the area here? We're looking for the area here, the area here, and the area here. Let's look at the formulas we know already. We know pi r squared. What does that represent? Hmm? Is that the area or is that the circumference? It's area. The circumference would be 2 pi r. Because think about it, we want 2 pi, which is the outer area here. And r is the radius. How big is it from the middle? So that's this is the area for a circle. The area of one circle. So we have pi r squared plus pi r squared. Now, this sheet has to be, it's the outer sheet of the can. It's gotta have a base and it's gotta have a height. So think about what's inside just the sheet of the can, just the outer shell of it. Remember, we only want the outside, so the circumference is 2 pi r. It's the derivative of the area, is the circumference. So we have the circumference of this circle. What are we missing? So we have the circumference. Is that 2 pi r? What else do we need? How high is it? So it's 2 pi r h. Is this going to be a volume or an area? This is important because is our variable going to be squared or is it going to be cubed? Let's see. We have this and this. We have 2 pi r squared plus 2 pi r h. We're looking for area, surface area. Because we want the area of that outer shell. This is surface area. And we want the least material. How do we find this? Oh, we also have, we know one other thing. Design a 1 liter can. So this can has to hold 1 liter. This is volume. So the volume equation of a can is what? you have the circumference, you have the roundness times the height. So it's two, or no, it's pi r squared times h. Because it's this circle and it goes up and down. And this is a solid area. Now, if I just make it stretch it out, I now have the volume. And how much does it have to be? 1 liter. Does it matter what kind of units we use? Not really. We could either use 1 liter, 10 deciliters, 100 centiliters. Well, since it's squared. Yeah, so it all depends on, so we're gonna use 1 liter. All right, so we know this. How do we relate this to this? What is h? Because the only thing we don't know here is h. Pi is the constant. R is the variable that changes. H is the only thing we don't know. We have h is equal to 1 over pi r squared. So we have our surface area is equal to 2 pi r squared, 2 pi r h, and h goes in there. One over pi r squared. So the pi's cancel and one of the r's cancel. So we have 2 over r. This is our surface area. So you see, once we drew the picture, now we have to start building our equation. We had the top and bottom, we have to get the surface area aside and figure out now the only variable we don't have is h. Because if you think about it, both of these are squared units. R squared, R times H is the unit squared. So now what do? We have the surface area. Two pi r squared plus 2 over r. Yeah. What are we looking for? The least amount of material. It's an extrema. Maximum minute. So how do we find extremas? The first derivative. Or dy, dA dr. We find it's either way it does. So we're taking a derivative with respect to r. So the first one's going to be 4 pi r. So we have 2r to the power -1. The derivative of that is -1r to -2. So we got -2 over r squared. We find the derivative. Now what? Find a prime. Then set a prime equal to 0. So I'll move this one to, oh, sorry, make it positive. So it's 2 over r squared equals 4 pi r. Multiply both sides by r squared. We have to solve for r. So r cubed is equal to 1 over 2 pi. How do we get rid of the cube? Cube root. Whatever that root has to be in that of both sides. So r is equal to the cube root of 1 over 2 pi. Whatever that number is, that's the answer. Yeah. The radius that gives us the least what? Material. We're not done yet, really. What kind of thing are we designing? A cylinder can. We found the radius for the circular part. How about the height? What is the height? Our height equation was 1 over pi r squared. Right. It's 1 over pi cube root of 1 over 2 pi squared. I'll just leave it at that. I mean, I could try to, because this would be 1 over cube root of 2 pi, rationalize, flip at the top and bottom, everything. So I could do that, but it'd be a lot of pain. Just plug this in the calculator. That'll tell me the height. Remember, yeah, whenever you design something, the first one we only did what sides get cut out, only one dimension. This one we have the circular and the vertical. Let's look at example 3. Oh, yeah, think about it. It's cheaper doing that than designing trial and error.
Yes. Yeah. You know, like, we were talking this one. I was talking about this in class. So it's like you think about grocery store would replace cashiers with like.
Yeah.
So sure, we're not paying out.
And then also the risk management, the loss management, how much people, because I've seen people at Walmart, they know they have dog food on the bottom part there. They purposely not scan it.
And so
Again, you got to scan this ice bar, that's worth $500.
Exactly.
Yeah.
So, yeah. Yeah, it's, you can't get away not having people. It's never gonna happen.
It's like, oh, so I guess then we can have, are you prepared to buy this entire case, this, 10 pounds?
And they do. People just put that in there and they scan one or two things to pretend they're scanning and then they walk out. Oh yeah, it's just amazing what people get away with.
It's funny if they maybe just apply the brain power.
Example 3. The rectangle is to be inscribed in a semi circle of radius 2. What is the largest area the rectangle can have? And what are its dimensions? Again, let's interpret this as a graph. A rectangle is to be inscribed into a semicircle of radius 2. And it has to be inscribed, so it has to be inside there. What's the largest area of the rectangle? And what are its dimensions? X and Y. So what's the domain? Domain goes from 0 to 2. So it's a closed interval 0, 2. So we have to look at, we're going to have to test both of those endpoints as well once we find the answer. Now we got to find the interior point. So now we got to figure out what the formulas are. It didn't give us that anything. So a semicircle is two squared minus x squared. The length of this box is going to be, the maximum has to be from this point X to 0 and 0 to X. So it's 2X. So the area is going to be base times height, which is 2x 4 minus x squared. Is everybody okay on where I got this information here? Okay, it's a semicircle. What's the formula for a semicircle? It's x squared plus y squared equals r squared. We know the radius is 2. So y is the height. If we have the x's, so move the x over there. So we have y squared equals 2 squared minus x squared. And then square root both sides. I'm sorry, I shouldn't have jumped through it so fast.
No,
Okay, we know that we have to be on the domain 0, 2. So we have to find our derivative. We're going to use the product rule. We have 2x 4 minus x squared to the power 1/2. This one's going to be 1/2 4 minus x squared to the power -1/2 times -2. So the derivative is going to be 2 times the square root of 4 minus x squared. Plus, well, that's a minus. The 2's cancel. X over square root of 4 minus x squared. The 2's cancel. This is a negative exponent, so it's x over 4 minus x squared to the power 1/2. I'm going to do that one. 2 times that minus 2x times this. I forgot that one. So the derivative equals 2 radical 4 minus x squared minus 2x squared over 4 minus x squared. So far, so good? Now, why is it minus? Because the derivative of the inside here was -2x. So this one became, it's negative. So negative times positive is a negative, there. All right, so let's fix that, let's clean that up. A prime equals 2, 4 minus x squared minus 2x squared, 4 minus x squared. Set that equal to 0. In algebra, in algebra, whenever you have fractions and equal sign, remove fractions. First, find the LCD. What is it in this case? What's our LCD? Yeah, it's our only D. Multiply LCD to each term. What is a term? A term is anything separated by a plus, minus, or equal. So we have 3 terms in this example. We multiply the LCD to each term. Third step, reduce. Because the whole reason we multiply by the LCD is get rid of the fractions. So we get rid of these guys. Multiply to get rid of parentheses, and then solve for your variable. 0 times anything is 0. Radical 4 times radical that is 2 times 4 minus x squared. Those are gone, so we have minus 2x. Zero. Radical times radical, they cancel each other out. So you just have what's inside. Radical x times radical x is radical x squared, which is just x.
When did the 2x leaves the 2x squared?
Oh, you didn't. You're right. Good point. Good catch. Good, very good catch. So let's get rid of parentheses. We have 8 minus 2x squared minus 2x squared. Move it over. So we have 4x squared equals 8. So x squared equals 2. X equals plus or minus square root of 2. So our possible answers for x are negative radical 2, and or positive radical two. What can you say about those? Can't be negative because it's not our domain. Our domain's between 0 and 2. So the only value we have is that. So far, so good. Remember, we have 3 points, 3 x's we have to check. We have to find a to the power, or a of radical 2, a of 0, and a of 2. We have to do all 3 of these, and we're looking for the least, right? The largest area. So we'll look at the biggest number. Remember, a was 2x square root of 4 minus x squared. So we have 2 times radical 2, 4 minus radical 2 squared, 2 radical 2, 4 minus 2, 2 radical 2, radical 2, it's 2 times 2 is equal to 4. And we'll plug those in there. 2 times 0 is 0, 0, anything is 0. Inside here, 4 times 2 squared, 4 times 4 is 0, 0. So our x value is radical 2, and the area is 4. That's the largest. Oh, no, that don't ask, what's our y value? What's the height? Oh, no, that's the height. This is the height we're looking for. What's the length? Because remember, the length formula was 2x. What we just solved here was for the height value, which is the outside. Now we want the length. Length is equal to 2x. Length is equal to 2x, which is 2 times radical 2. And height equals radical 2. And area equals 4. Cover that one later. Examples of economics. We'll come back and do the light speed of light one later on. R of X is the revenue. From selling X units. C of X is the cost of producing X units. P of X is the profit. From producing and selling X units. P of X is the revenue, how much money you got, minus how much money it cost. All right, so that's what, example 5. Also, whenever you see the word marginal, that means a derivative in economics. Suppose the revenue was 9x and the cost function was x cubed minus 6x squared plus 15. X equals millions of MP3 players. Produced. Is there a production level that maximizes profit? Because it said maximizes profit, that tells us what? Extrema. So that means we're looking at the first derivative, right? So we have, let's see this. We have R of X is equal to 9X, which means R prime of X is equal to 9. The cost function is X cubed minus 6X squared plus is 15X, yeah, 50X. 6X squared plus 15X. So the marginal cost is 3x squared minus 12x plus 15. And remember, profit is equal to revenue minus cost. Here's an interesting question. When do you start making money? Right. So what happens when revenue and cost are the same? You're making no money. So, well, we're breaking even, right? So you break even when the profit equals 0, which that means is the revenue equals the cost. So far, so good. But it also works when we deal with the marginal, with the change. Since we're trying to find out, this is just one time. This is the function is just one time. What we're looking for is the derivative of these things. We're looking for the maximum profit. So maximum profit has to be the derivative. So that means when the derivatives equal each other. So R is 9, R prime is 9, C prime is 3x squared minus 12x plus 15. And yeah, I think you said it's called the break-even point. What we're looking for here is at what value X will our revenues and our costs be the same. Anything after that will be profit. So we make this equal to 0. 3x squared minus 12x. So subtract 6 or 9 from both sides, we get a 6. Three, four, so it's not going to be factorable, but we can divide everybody by 3. So we get 0 equals x squared minus 4x plus 2. A is 1, B is -4, C is 2. Put it in the Pythagorean theorem. So negative of a -4, -4 squared minus 4 times 1 times 2. Four plus or minus square root of 16 minus 8 over 2. 4 plus or minus square root of 8 over 2. Which is 4 plus or minus 2 square root of 2 over 2. 2 plus or minus square root of 2 over 2. Which is 2 plus or minus square root of 2. Let me write it on the other side. Is everybody okay up to here? I'll do the Pythagorean theorem on the other side, I'm sorry. So we had 0 equals 3x squared minus 12x plus 6. I factored out a 3 from everybody. Labeled A, B, and C. And use Pythagorean's theorem. Negative of a -4. -4 squared. 4 times 1 times 2. -4 squared is 16 minus 8. 4 plus 16 minus 8 is 8. This is why I lost you mostly. Look at this. 8 is made up of 2 times 2 times 2. So if we have the square root of 8, which is square root of 2 times 2 times 2, if you have a pair, they come out in front. Because it's the square root of 4. So that's what gave us 4 plus 2 square root of 2. Well, yeah, and I divide each, since they're coefficients, I could factor it out. I factored out a 2 out of the top. And that cancels. So our x values are 2 plus or minus square root of 2. And since we're looking for maximize the profit, plug them both in there. How can we tell without calculating, without doing this part, how can we tell which one of these? Remember, our answers are going to be either that and or that. Because remember, we're looking for our derivative set equals 0. So these are our extrema points. How do we determine which one's maximum, which is minimum? Without doing this. Second derivative test, concavity. Once we find the second derivative, plug these in there and see which one's positive, which is negative. We want the maximum one. So let's look at that. So the profit function is R minus C. The R function was 9x. And the C function was x cubed minus 6x squared plus 15x. Px is 9x minus x cubed plus 6x squared minus 15x. Negative x cubed plus 6x squared minus 6x. What can you tell me? Because remember, our x values we're looking at are 2 minus radical 2 or 2 plus radical 2. If we look at a number line, here's 2. This is 2 plus radical 2, and this is 2 minus radical 2. What do we know about this graph? It's a cubic function, which means it looks like this. But it's negative, which means it looks like this. That means the extrema on the left is going to be the minimum, and the extrema on the right is going to be the maximum. So our x value we want is that. So that's going to give us the maximum return, maximum profit. Again, referring back to algebra, most of you can't, because we could have found the derivatives, the second derivative, and then plugged them in there. That's extra work. Or if we know the basic rules of algebra, that the cubic function looks like this. Negative, you flip the direction. I know, it's kind of like you wish you knew what you needed to know now in algebra so you could pay attention even more. Because a lot of times people in algebra say, oh, this is easy. I remember this in high school, so I have to keep on going. And same with trig. I did it, but I don't need this. But then now, how much do I really need it? The last one. Example 6. Cabinet maker. Uses cherry wood. To produce 5 desks each day. Each delivery of one container of wood is $5,000. Whereas the storage of that material is $10 per day. Per unit stored. Where X equals, no, where a unit is the amount of material needed. To produce one desk. Now to the questions. How much material should be ordered? Each time? And how often should the should it be delivered? To maximize her average daily cost. Between deliveries. Yeah, now I agree with you.
Yeah.
Cabinet maker uses cherry wood to produce 5 desks each day. Each delivery of one container of wood is $5,000, whereas the storage of that material is $10 per day per unit stored, where a unit is the amount of material needed to produce one desk. How much material should be ordered? each time, and how often should it be delivered to maximize her profits, her average cost. So let's look what this means. So what are we looking at? We're looking at cycle cost. Each time she purchases it, what is the cycle cost? What is it made up of? Delivery costs plus storage cost. So let's look at, we have to define what X is going to be. We're looking for how often. So X equals number of days. And how much does she have to order? To order five of those. She must order 5 of those to have enough material. Now, the average storage, how do you find average? She either has nothing or she has 5 times that much. The average is add those together and divide by 2. So the delivery cost and then we have to look at the storage cost. We have to put them together. So what's the delivery cost? $5,000. And storage is 5x divided by 2. Remember, the delivery cost is a one-time thing. The storage, on the other hand, is dependent on what? The average storage cost times how many days it's going to be stored times the cost. So this is the amount in the storage, the number of days, and the cost of storage. So the cycle cost is equal to 5,000 plus 5x over 2 times x times 10. So this is the cost The delivery cost is $5,000. But when we're looking for the long scheme of things, it has to deal with also how many times we do it. So it's a cost, remember, it's the cost per cycle. How many days? So there's our equation. What's our domain? We can't, X cannot equal 0 because it's 0 on the bottom. Can X be negative? No, so can it be positive? Because these are the number of days. So X is strictly greater than 0. That's our domain. So whatever we get when we do our answers, we have to have positive answers only. So we have to find the marginal amount. So we take the derivative. X to the power -1. The derivative of 25x is 25. This comes out in front. So it's negative 5,000 x to the power -2. So it's negative 5,000 over x squared. Set that equal to 0. So we get 25 is equal to 5,000 over x squared. Multiply by x squared and divide by 25. $25 goes into 50 twice. So square root both sides. X is equal to plus or minus the square root of 200. Since we can't have negatives, the only X value that can work is the positive 200. Okay, so the question's asked, how much material should be delivered each time? And how often should the material be delivered to minimize her average daily cost of production? So that's the amount because we had no other choice. And then we just calculate it. We can figure out the cost. Right, yeah, the C function to find the cost. So let's look at that. The C of the square root of 200 is equal to 5,000 over the square root of 200 plus 25 times the square root of 200 we could combine these at a common denominator. We got 5,000 plus 25 times 200. Oh, 707.11. This is the critical point value. Let me put that over here. Critical point value of the average daily cost. That's what that first one says.
So that's the average cost of. No,
Yes, that's the average daily cost. To order it, store it, and make it for everything. Yeah.
square root of 200, is the X value again?
That's the X value. X value is the number of items we're looking for. Oh, what is the first derivative find for us? We had the first derivative is negative 5,000 over X squared plus 25. That tells us 0. Which is what we wanted to tell us, remember? Because the first derivative, we're looking for, where is it maximum or minimum? That's checking it there. What is what? Square root of, where is that? Clear that. So 200 square root of that. What does that represent? So you'll get the minimum, it occurs at square root 200. Which is, remember, X represents the number of days. So you'll get the minimum when we do our orders and store it for 14.4 days. So approximately 14 days. So how often should the deliveries be made? She should expect the delivery order of this. Remember, the question asked, how much material should we order each time? She should order 5x, which is 5 times square root of 200, which is 5 times 14.14. We're looking at number of days. So we're looking approximately at 70. So she should order 70 pieces of wood every 14 days. Yeah, finding the derivatives is easy. Understanding what they mean is the hard part. So that's why I always have to refer back to what is the question asking? Because we have to find what pieces do we need from what we've found already. Other than that, that's it.
How was it determined? Is the derivative cardinal number?
Yes,
How was that?
because
And then like.
and it's the rate of change. It's your cost. How is it changing? As you're producing more, what is happening to your cost? What happened to revenue as you produce more? As your order changes, the number of whatever X's, that'll change your revenue. The profit is a change of that. Now, why is that a derivative? Because you're talking about the change of orders. So, and that's why whatever the rate of change is, you put the X in there and that'll tell you what your current state is.
So it's the. I get it, so it's like, if, like with physics, velocity being a derivative and then acceleration being the next derivative.
Yes.
Which is rate of change of the velocity rate, and then there is the rate of change of.
Yes, I mean, everything we keep on going further and further and further. Each of it has its own thing that we keep on going. So this, but unfortunately in business, you can't go further than, I mean, once you do the rate of change of, what are you gonna do after that?
Right.
The rate of change, how fast you're gonna change your orders?
Yeah, exactly.
We only have one more section left to do in chapter 4. We'll do that next week. It's called Newton's method. We are now going to stop using just number our stuff. We have to use a calculator now, a computer. Because in this kind of situation is you'll get to a point where you can't solve the equation. It doesn't have a solution. So you have to put it through, you have to pick your first value to start off with. This is what you think the answer is. You plug it in the formula and it'll keep on working it out. It'll spit out an answer. Well, you take that answer, that's your next input. Do the work, get the next answer, and you keep on doing that. It's called iterative methods until you get the final answer. Until it approaches something and doesn't change anymore. That's what we're going to do next week. And to be honest with you, I really think we should be able to finish everything next week. Because, well, worst case scenario, we'll have to meet on Monday, the week after, but we're pretty close. We have one more section in chapter 4 and 6 sections in chapter 5, and we're done.
Do we, is there not meeting tomorrow? Or meeting-
No, I promised y'all a Thursday off
Oh, that's right.
because I kept you on literally way too long on that other day.
Or. No, it's good, it's good. I did, I had to catch up on chapter